Imagine you are an early human herder living in the Stone Age. The sun is setting, and you need to make sure every single animal has returned to camp. But you have a problem. You don't know the word one, you don't know the word hundred, and you have no idea what the digit 5 looks like. To track a herd, monitor trade goods, or even count the passing moons to predict the seasons, you need a standard sequence. That means a fixed order of ideas you can match against the real world. But early humans didn't have our modern counting systems to rely on. They had to distinguish between two things: the number, which is the invisible concept or quantity, like a physical group of dots, and the numeral. A numeral is simply the written symbol we invent to represent that invisible idea. The concept of 5 is completely separate from the shape of a 5 drawn on a page. The entire history of mathematics is a story of humans slowly upgrading those numerals to solve increasingly complex problems. The very first upgrade was physical. It's called one-to-one matching. For every single object you want to count, say a cow, you keep exactly one stick or one pebble. Later, you match each stick back to a cow. If you have a stick left over, you know an animal is missing. This system works perfectly, in theory, forever, but it fails physically at scale. Try managing a herd of 1,000 cows by carrying around 1,000 heavy wooden sticks. People tried other workarounds. Some cultures used a sequence of sounds, mapping numbers onto the letters of their alphabet, so A equals 1 and B equals 2. That is much easier to say aloud, but the system breaks the moment you count past the number of letters you have. Others use their own biology. A group in Papua New Guinea maps numbers onto a specific sequence of points all over their bodies, allowing them to count well beyond just 10 fingers. Yet, relying on physical objects, spoken letters, or body parts isn't sustainable for building a complex civilization. Humans needed a permanent written system that could scale up indefinitely. The solution was carving marks into wood or bone, one notch per object. We still have evidence of this. The Lebombo bone, found in South Africa, is roughly 44,000 years old. With its 29 carved notches, it stands as one of the oldest known mathematical artifacts in the world. But street tally marks hit a biological wall. Look at this diagram. Our brains can instantly recognize quantities up to about 4 or 5 without having to count them one by one. Anything beyond that begins to blur into an indistinguishable pile. Because of this visual limit, ancient cultures separated by oceans, like the Gomolgal people in Australia and the Bakayiri in South America, independently invented grouping. They assigned names to only the numbers 1 and 2, and then built larger chunks of numbers by combining those small ones together. 3 became 2 plus 1. This habit of grouping by 5 is still how we count today. When you draw 4 vertical tally marks and slash a 5th line diagonally across them, you are using the same shorthand developed by these early cultures to bypass the limitations of human sight. The Roman numeral system took this grouping idea further by creating landmark numbers. Instead of endlessly stacking small groups, they invented single letters to represent specific larger chunks: I, V, X, L, C, D, and M. To construct a number like 27, you break it down into these largest possible landmarks and stack them together. That gives you 10 plus 10 plus 5 plus 1 plus 1, XXVI. Later on, they refined this by using subtraction to avoid repeating too many symbols, writing IV for 4, meaning 1 less than 5. Though, as you can see on many historical clock faces, ancient scribes and clockmakers weren't always consistent about using that rule. By compressing massive quantities into a handful of standardized letters, Roman numerals allowed a sprawling empire to track vast amounts of wealth, taxes, and legions with just a few strokes. So if this system was so efficient, why don't you use Roman numerals to do your math homework today? Because they have a major weakness: arithmetic. Adding or multiplying them forces you to manually hunt down scattered symbols, regroup them, and convert them, like turning 5 C's into a single D. This mathematical bottleneck meant humans had to find a better way. Later civilizations, including the Egyptians, would push mathematics forward by discovering the base system, where numbers follow a strict, predictable mathematical pattern. Even so, the Roman grouping system never disappeared. We still use it for movie copyright dates, clock faces, and for numbering royal titles, like Queen Elizabeth II. We started with a physical pile of sticks, carved tallies into ancient bone to keep permanent records, learned to group those tallies into chunks, and eventually compressed them into shorthand Roman symbols. Now it's time to test what you've learned. Grab your notebook. Here's a quick 5-question revision quiz from us at Special 5 Online Tuitions to lock in today's concepts. As you write down your answers, remember that every single digit you draw is the result of 40,000 years of human problem solving.